So welcome along, ladies and gentlemen, to your weekly SETI seminar series talk. Today we're joined by Sigrid from Stanford University. Sigrid got her BS in Central New York at University of Rochester in physics and astronomy, and then master's in physics from UT Austin. And then she did her PhD in space physics at Boston University. She then worked at MIT Lincoln Lab and has also recently moved from her job at Los Alamos National Laboratory in New Mexico, where she was working on satellite systems for situational awareness in space. She particularly is interested in broadband-tuned radio frequency methods of tracking satellites, and she has recently developed a technique for using RF to detect pulses of EM, of electromagnetic energy, that are given off when particles impact with spacecraft. And that's what she's going to talk to us about today. So if you'll join me in welcoming Sigrid.
Thank you, Adrian. And thank you, everyone, for coming here today. I'm going to be talking to you, as Adrian said, about what I think is a really exciting, fascinating topic, which is understanding meteoroids. And I hope by the end of it that you also share a little bit of that excitement. I just want to tell a quick story about how I actually got involved with meteoroids, because it was actually a complete side issue from what I was doing when I was a staff scientist at MIT Lincoln Laboratory. We were trying to detect things using airborne radar. And one of the big issues is that we had a lot of clutter that we had to get rid of. And one of those things that was this clutter were these meteoroids, these little tiny particles coming in and creating these shooting stars that everyone knew about. And I was really annoyed because it made my job a lot harder than what it would have been normally. Fast forward a couple years later, and I was stationed at the Kwajalein Atoll, again working for MIT Lincoln Laboratory as a launch analyst. Here we were trying to basically make sure that all the satellites that were launched into space went where they were supposed to. And I got this call from General Worden, who is now the director of NASA Ames, saying, okay, well, the Leonid meteor shower is coming. I'm really worried that it's going to take out my space assets. What can you do? So again, this whole concept of meteoroids and space surveillance, or surveillance in general, was a repeating theme. And it was at that point that I thought, this is something interesting. I want to go look at it a little bit more, and it eventually led to my PhD, and now a professorship at Stanford. So I tell my students that, don't ever discount anything you're looking at. It could actually end up making your career. Okay, so with that introduction, why am I looking at meteoroids? Well, I think that they're, again, a fascinating topic, and there's a lot of reasons to study them. My particular group at Stanford is really focused on understanding when a meteoroid hits a satellite, what could potentially happen. We know that meteoroids hit satellites all the time. And the first, probably most famous example was the Olympus communications satellite, which was lost power during the peak of a Perseid meteor storm back in 1993. And here's an image of it. Now, even though it failed during the peak of a meteor shower, there was no detectable momentum transfer, meaning whatever hit it wasn't big enough to actually be detected. Yet they think that what happened was that this particle impacted and caused an electrostatic discharge that eventually took out the system, and it was considered a complete failure. Back in 2002, the Jason satellite also suffered a power or electrical anomaly, now known associated with an impact. The Jason satellites at about 1,300 kilometers orbit, they saw about a 30-centimeter change in its semi-major axis. And for 5 hours after this, it experienced a power spike. We're not sure what hit it, whether it was a piece of space debris or a meteoroid, but we do know that it was impacted and then created this electrical anomaly. The Landsat 5 satellite in 2009, also during the peak of the Perseid meteor shower, suffered a loss of gyrostability. And they were able to recover, and we can't prove causation, but it was correlated with the peak of this activity. And then finally, probably all of you have heard about the Galaxy 15 anomaly. This is a geobird that had been drifting in its orbit for quite some time. We still are not actually sure what happened, what caused it to basically go spinning out of control or losing its attitude. And all we know now is that it was due to what's called an electrostatic discharge. Again, some type of electrical anomaly. May or may not be associated with some type of space weather effect. So for my research, even though, again, there's many reasons to study meteoroids, we're really focusing on what could it potentially do to our space assets. More importantly, can we prevent it so that we don't really have to worry about this effect in the future? So the outline that I'm going to go over today is what's the motivation? Can we go over a little bit about why we like to study meteoroids and their larger cousins, I should say, asteroids and comets? How often are we hit? Then I'll give you just a little bit of background on meteoritics. It's a very old subject, and yet, again, there's so little that we know about it. Then I'll talk about when meteoroids come into the atmosphere, how do they form these meteors, and then how can we study them and understand their properties. And then I'll end with an in-depth discussion on how we're actually looking at the interaction between meteoroids and satellites. Okay, but first let me just introduce the terminology to you, just so in case you're not familiar with what I mean when I say an impactor or a meteoroid. Now, on the small end of things, we either delineate in terms of size or we sometimes delineate in terms of origin. For my purposes, we're going to do it in terms of size, where dust is basically anything smaller than about 62 microns, and a meteoroid is somewhere between 62 microns and 0.3 to about 1 meter. They can either originate inside of our solar system or they can originate outside the solar system. And the densities could either be rocky or they can be ice-like. And again, there's this whole suite of particles, and we're still not sure exactly where or what types of particles we're seeing. Now, on the larger side, the only distinction between a meteoroid and asteroid is really size. Okay? And there's lots of definitions, but nominally we'll say about 0.3 meters and larger is an asteroid. Some other people say, well, if it has a name, it must be an asteroid. If it doesn't, it must be a meteoroid. So you'll see a lot of debate in the literature. It's like the whole discussion about Pluto. We're still not really sure on how to define these. On the same size, the comets, as you probably know, there's a lot of discussion now between what's the difference between an asteroid and a comet. We used to say, well, comets have tails, asteroids don't. Well, actually, now we're finding asteroids do have tails. So again, but for just a simplified definition, I'm going to say that comets and asteroids tend to be interplanetary, and comets tend to be more ice-like than asteroids. But again, for this talk, we're going to be focusing on the really small ones, the ones that come in all of the time, that are far more likely to damage our satellites than, let's say, an asteroid or a comet. Okay, the good, the bad, and the ugly. Okay, why do people care about asteroids and comets and meteoroids? For those of you who watch movies, for those of you who watch TV, you'll know it's all over the TV. People love to think about death and destruction and how we could potentially be taken out by an asteroid similar to the dinosaurs. So I want to talk to you about what are the good things associated with asteroids, because often you don't hear about these things. The main theory, I would say, is that the reason why the continents formed is actually due to this period of heavy bombardment, which occurred between about 3.5 to 2.5 billion years ago. There are 9 major strikes that we know of, probably a lot more that we don't know of that hit the oceans. But we used to think that these asteroids actually suppressed continent formation. Now we know that when these asteroids hit, particularly on, let's say, something that has like volcanic activity associated with it, even though it's suppressed locally, what would happen is that these continents would then start to form underneath the Earth's crust in a more cohesive fashion, because you would have many volcanoes now acting basically collectively to make these land masses as opposed to just one volcano. So the theory is that actually this period of heavy bombardment actually probably helped form the continents. And then on a very controversial side, it could also be the reason why we're all sitting here today. Now, whether you believe or not that meteorites actually can carry life to Earth, what is irrefutable is the fact that we have the possibility that meteorites have the possibility of carrying things like amino acids and I would say basic biological material. 4 billion years ago, Earth was essentially lifeless. And again, we went through this period of heavy bombardment, and then we know that life started to form. Meteorites do travel in interstellar space. We know they are irradiated by neutral stars. and neutron stars, sorry. And these neutron stars actually emit and alter the amino acids on the meteoroids. The majority of life on Earth has something which is called this left chirality. And by traveling through interstellar space, these meteoroids are getting preferentially subjected to these neutron stars, which then cause them to have this left-handedness or this left chirality associated with it. So again, very controversial, still very speculative, but the possibility is there. Now, the bad impacts. The other thing is that, as you may or may not know, meteorites actually do hit people on Earth. Luckily, it's very rare. We do know of instances where they've crashed through buildings. A very famous case is this rather disturbing picture that you see here on the bottom left. Her name is Elizabeth Hodges, and in 1954, she was sitting in her living room when all of a sudden this big rock crashed through her ceiling. And it hit a table, bounced off, and then hit her in the hip, causing this, again, this disturbing bruise that you see here. And it has been conclusively decided that this was actually a meteorite, quite a large one. Last year, or a couple years ago in Germany, there was a little boy walking on his way back from school when he claimed to have been hit in the hand by a meteorite. People thought he was crazy, but they've since done analysis on the object and have found that, yes, indeed, this was a meteorite. It bounced off the ground and hit him on the hand and gave him a little scar. And then there was also this famous story about a dog in Egypt that was actually killed due to a meteorite strike. We're not sure if this is true or not, but there's a very elaborate story associated with it. So even though it's very rare, meteorites can actually impact humans on Earth. But more often, as I explained about the Olympus anomaly, is that they hit satellites, as you just saw. Now, NASA and other organizations have spent a lot of time characterizing the mechanical damage associated with impacts on a satellite. But as you can see here through this artist's conception of what probably happened to the Olympus communication satellite, a meteorite strike on these very large solar panels, which is most of the real estate on a satellite, could cause perhaps an electrostatic discharge, a discharge on the satellite, or even something a little bit more nefarious called an electromagnetic discharge or an electromagnetic pulse, which could potentially take out satellites. So again, this is the focus of this research, is not can we just understand how often we're going to get hit, but what's going to happen if we get hit, and can we prevent it in the future? And then, as I already mentioned, people are very interested in understanding meteoroids and asteroids because we believe that this is the probably most likely reason why the dinosaurs went extinct. About 65 million years ago, there was an impact by a 15-kilometer asteroid off the Yucatan Peninsula in Mexico. It's called the Chicxulub crater. And even though we're looking at other things like, as far as mass extinction goes, it's just changes in the environment, volcanic activity, still this asteroid impact, which we know happened at the time that mass extinction occurred with the dinosaurs, is the most likely reason. And NASA, as well as others, are saying, okay, well, can we monitor the skies now so that we make sure we know if something's going to hit us, and then put a plan in place to push it out of its way or blow it up, do something to prevent it hitting Earth. Luckily, the bigger it is, the less likely it is to hit the Earth, as we all know. Otherwise, we all wouldn't be here. So if we're looking at asteroid diameter or energy released as a function of how often it happens, you can see from this graph that if it's something 4 meters or less, happens about once a year. If we're talking about the Chicxulub crater, again, the one I just described, that's about every 100 million years or so. So the most recent, I would say, large-scale impact occurred over Tunguska back in the early 1900s. This was about a 20 to 30 meter asteroid. Some people do think it's a comet. And as you can see, the amount of energy released was about, I would say, 10 to the 2 megatons of TNT. The Barringer crater in Arizona, the Arizona Impact Crater, was more on the order of 30 to 50 kilometers across, or meters across, sorry. And that happens about every 10,000 to million years. Okay, this one happened about 50,000 years ago. Now, the problem with this curve is that clearly it doesn't follow a straight line. Okay, this is based on very, very limited data. It's based on extrapolating, doing a lot of modeling. So the problem is that we're just not sure when the next big one's going to hit. And again, this is why a lot of people focus their efforts on this. The size particles I'm worried about, however, are microgram particles, okay? Things you can't even really see with the naked eye. These come in at the tune of about 100 billion a day. So even though there's no chance of us being hurt by these particles, certainly our satellites in orbit are much more likely to get hit by those than it would be by even a 4-meter size asteroid. So why study meteoroids? I already mentioned in terms of astronautics, which is what we're interested in, causes damage. We could look at it in terms of clutter, which is why I originally started looking at meteoroids so many years ago. And in particular, I'm very interested in putting together satellite missions to basically understand these particles. Can we figure out if life on Earth came from meteoroids? Can we figure out if the next asteroid is going to hit us? A lot of my colleagues, however, look at meteoroids in terms of understanding atmospheric physics. They're great probes into the lower atmosphere. We can determine things like what's the neutral densities at 100 kilometers altitude, what are the temperatures, what are the winds, and how responsible are they for all the heavy metal layers that we see? How much dust is being produced? And then on the astrophysics side of things, we can characterize interplanetary objects. We can look at things like the origins of solar systems and how much meteoroids and asteroids played a part in that. And personally, I think a very exciting topic is characterizing interstellar objects. How many are coming from outside our solar system? Are we really made of star stuff? And again, this is very preliminary. I'll show you some data later, but it seems like at least 5 to 10% of the objects we see do originate outside of our solar system. So another controversial topic. But again, for this talk, primarily focusing on the astronautics part of it. Okay, so let me give you just a little bit of background and history on meteoritics. As I mentioned, this is a very, very old topic, and yet there's still so much we don't know about it, which I think is very interesting. So way back in the time of Aristotle, he has a very famous quote, and that meteoroids, the whole concept of this is absurd, because he said rocks could not fall from the sky because the heavens are perfect. Of course, right? And a lot of people believe that, even though you'll find many coins about meteorites. People found them at that time. They thought, oh, these are rocks from space. But Aristotle and other great thinkers said, no, you guys are stupid, don't even go there. The French Academy, back in the 1700s, said, these were the main thinkers of the time. People looked to them to say, okay, what should I be thinking about? What makes sense? And they said, well, stones cannot fall out of the sky. And then Jefferson, very famous quote, said, I would sooner believe that 2 Yankee professors would lie than that stones would fall from the heaven. So all these very, very intelligent forethinkers were saying, okay, well, this is really dumb. You guys shouldn't be thinking about it. So consequently, if you go to a museum, it'll be really hard to find a meteorite that dates before the year 1700, 1800. It's not because people didn't find them. It's because all the museums threw out their collections because they wanted to make sure that they were part of this movement saying, okay, we're part of the smart people, right? So it's like this collective mentality. And again, this is so important for students, is that when you're going against something that's the general thought at the time, I want them to pursue it. I want to push it because these very smart people turned out to be wrong. So how did we figure out they were wrong? Well, we collected data, right? Meteor showers happened. And people looked up, and particularly in 1794 and 1795, people in Italy and England said, oh my gosh, there are things coming from the sky. What else could this possibly be? And in 1803, there were thousands of rocks falling from the sky. And it was basically irrefutable at that point. There's no other reason or no other explanation to say why we're seeing all these bright streaks in the sky. So the French Academy changed their stance, and all of a sudden, the rise of meteoritics happened. A very famous German scientist, Ernst Chladni, proposes that, okay, these have an extraterrestrial origin. These meteorites are not coming in from Earth. Some people had said, well, maybe these are rocks being kicked up by other parts of the Earth and then coming back down into our atmosphere. And he said, no, this is coming outside of Earth's system, and we should really be focusing on this. So in 1802, meteorites were established as distinct from terrestrial rocks. And then, as I mentioned, people really started to study these. Okay, so meteoroids are usually classified as either showers or sporadics. And probably all of you have heard of things like the Perseid meteor shower or the Leonid meteor shower. It happens at the same time every year, appears to come from the same position in space. And if you happen to be looking outside at the time, if you see this movie, you'll basically see lots of flashes in the sky These are little bits of dust coming in and burning up and creating plasma. Now, as I mentioned, they occur at the same time because they're usually associated with one parent object, most likely a comet, perhaps also an asteroid. So the comet comes by in its orbit, it deposits fresh debris. When Earth's orbit intersects the comet's orbit, we get a meteor shower. If the comet has just come by, like the Leonids back in 1998 that General Worden was worried about, then it turns into a meteor storm because there's a lot more fresh debris. And it's named for the radiant. So the Leonids don't obviously come from the Leo constellation. They just appear to come from the Leo constellation due to the Earth's alignment. Okay, so even though you may have heard about the showers, it's actually the sporadics that cause the most trouble. Yet no one even really understands sporadics. We didn't even really start looking at this till about a decade ago. Sporadic, as the name implies, means that it comes in all the time. It could come from anywhere in space. And it's basically due to gravitational focusing within the Earth's solar system. So dead comets, asteroids that are no longer producing a lot of debris, get gravitationally focused within the solar system and have this continuous rain down on the Earth. So actually every morning at 6 a.m., as the Earth's coming by in its orbit, it's plowing up this debris, just like a bug on a windshield effect. And you will see, as I mentioned, billions of meteoroids at the tune of 1 a second if you're using a radar, which if you extrapolate to basically over the whole Earth is over 100 billion that are microgram size or larger. And this was a huge result that we came up with 10 years ago because people didn't even know that these particles exist because they're so small. You can't see them with the naked eye. You need instruments to detect them. And yet they're large enough to cause damage. So what happens when these particles come into the atmosphere? Well, they're coming in very, very fast, between 11 and about 73 kilometers per second. That 73 kilometers per second is a sum of the Earth's orbital velocity as well as the escape velocity for a particle in orbit about the sun. So they can certainly be faster, but then we're talking about things that have an interstellar origin. They are depositing between 3,000 to 300,000 tons per year. The reason why there's such a large error on here is because depending on what instrument you're using to observe, you get a much different answer. This gets into this whole area of selection effects in the instrument. But what happens is it's a pretty simple process. The meteoroid comes in, if you'll forgive this little cartoon, it heats up and it sheds off ablated atoms that then collide with the background neutrals and forms a plasma, which is just the ions and electrons. So what most people don't understand is that when we use radars to detect meteors, we're not actually ever scattering from the meteoroid. We're scattering from the plasma. And it takes a lot of complex modeling to go from detecting a plasma to figuring out the properties of the particle that actually form the plasma. These plasmas are formed between about 70 and 140 kilometers. Just so happens that that's the right altitude. There's enough neutral densities to form a plasma, but it's not too low down that the meteoroids have burned up. So there's this sweet spot in the atmosphere, and that's why we usually see them around 100 kilometers. Enough neutral density, still enough energy associated with the meteoroid to actually form something. And we categorize it in terms of what type of plasma it is. We call them heads if they're right around the meteoroid. They're very small, they move very fast, but they're hard to detect. Or trails, which are the ones that you can visually see when you go out at night. These are the ones that go on for many, many kilometers and have quite a bit of signal strength to them. All right, so let's talk a little bit more about meteoroids in the atmosphere. As I mentioned, it's a really hard problem to go from measuring a plasma to understanding the properties of the meteoroid that actually formed the plasma. The first thing you need to do is to model exactly how does a meteoroid form a plasma. Now there's a huge amount of energy there. Remember I said 11 to 72 kilometers per second, so way faster than orbital debris, which are going about 7 kilometers per second. What we think happens is that there's a mini shock that actually forms in front of these particles, even though they're way smaller than the atmospheric mean free path. Okay, so again, think microgram particle, really tiny, going really fast. And what we've done is put together what's called a particle in the cell simulation to try to understand how this plasma forms. So I won't get into all the details of it, but if you look at this movie, you'll see that this is actually the meteor. This is the plasma formed when the particle comes in, hits the neutrals, and gets ionized. So the meteoroid is at the very front. You can't even see it. The red are the electrons, the blue are the ions, and then the black are the neutrals. And this cloud is the meteor. Again, this is a microgram particle. I believe for this one it's going about 30 kilometers per second. And we're basically looking at how much energy is released upon each impact. It turns out it's on the order of about 6 eV or so. Okay? So if you take it over how many impacts occur each time the meteoroid's traveling in space as it hits all these neutrals, it's on the order of about 600 eV. Okay? 600 eV per neutral molecule is released. Huge amount of energy. Most of that energy goes into actually ionizing itself as well as the background neutrals. The second part of that is even after you have a model for that plasma, you then have to understand how does a radar wave interact with that model. So if we take this semicircular and model this as part of the plasma that's formed when a meteoroid comes in, again, this is called the head or the head ectoplasma, we can assume from our model that the plasma density basically falls off with distance from the meteoroid, which makes sense. You can then put together a model to understand how does that radar wave interact with the meteor plasma. What you see here on the bottom right is that model. This is the frequency of the plasma, or how dense it is, as a function of how big it is on the x-axis, and it's color-coded for the reflectivity you would expect from a radar wave incident on this meteor. Again, I won't get into the details, but what you'll see here is that if it's a really big, really dense object, you have a reflectivity that's about equal to 1. This is similar to scattering from any hard conducting target. If you have a meteor that's very small and not so dense, it has a much lower plasma frequency, then your reflectivity is consequently very small, in the order of 10 to the minus 7 or 10 to the minus 8. So using a combination of these two models, the PIC simulation on how a meteor gets formed, and the electromagnetic scattering on once it's formed, how does the radar interact with that, we can then back out the properties of the meteoroid. So that's why I say whenever you look in the literature and say, someone says, okay, this is the amount of flux that comes in, or this is the properties of the meteoroids, always be cautious reading it, because there's a lot of hand-waving and a lot of modeling that usually goes into these publications. I, of course, would never do something like that. So. But what do we see? Okay, I said, gosh, over 10 years ago now, I was sitting on the Kwajalein Atoll. For those of you who are familiar, it's this tiny little top of a volcano in the middle of nowhere between Hawaii and Guam. It's like almost an 8-hour plane ride west from Hawaii. And the island is so small that you actually live on the southern part of the atoll, and you fly up every day in this little commuter plane to the northern part where the radars are. And our primary objective there is to stare west and basically track anything that's being launched from places like Russia or China. And again, just make sure that we know where things are going. But as General Warden, shouldn't say general anymore, as Dr. Warden said many years ago, he was worried that all this tracking that we're going to do is going to be for naught, because the Leonids are going to come and take out many of these satellites that we were trying to track. So I have to say, by far, my favorite radar to use for these meteor studies is Altair. This is the radar that's out of the Kwajalein Atoll, because it is a very expensive, well-calibrated radar, which now as an academic I could never afford, but at the time I had free access to. And we were able to take Altair, which is normally used for these other missions, and turn it into a pure science radar. And because of that, we've gotten some absolutely amazing data. If you happen to be sitting at Altair, this is what you would see if you would look up at any point and go in the meteor regime. Again, remember, about 100 kilometers. So what you're going to see here is just a movie of a meteor coming through. This is the VHF, very high frequency, and this is UHF, ultra high frequency. So as you see, it came in, and it just deposited some plasma there, and you see some spikes going up and down. On the bottom, again, is the UHF, and on the top is the VHF. So just from observing this, you could see that it has a really strong frequency component. Depending on what frequency you're using to radiate it, you'll get a much different response. So this VHF trail goes on forever, the UHF disappears. But this is a huge source of clutter, right? If you're trying to track something, yes, sorry, in the back. That's real time, yep. I could start it again. This is just time. Okay, so this is our incident radar pulse, and this is time, basically amplitude.
And the horizontal bars below it indicate the range gate corresponding to the altitude?
Exactly. Yep, thank you. Yep, so I had opened up my range gates between about 70 and 140 kilometers altitude, even though most of the time the meteors reside in that central part near 100 kilometers. So this is a huge source of clutter, and an interesting aside is that people knew this years ago, back in the 70s and 60s when Altair was first built, that if they started to open up their range gates in this altitude, they would see these meteors all the time. But that knowledge got lost. So when I was there back in late 90s, it was like we reinvented the wheel. People knew this years ago, and they just happened, we forgot about it. It wasn't published, and therefore we basically spent a lot of time just redoing what people had already done back in the 60s. Okay, so some other radars that we use are the Arecibo Observatory. I was just speaking with one of the staff scientists there this morning. He's discovered some amazing data. We've taken our Arecibo, and using the simultaneous VHF, UHF frequencies there, we've been able to irradiate these meteors and find out what the frequency component is as well. Unlike Altair, Arecibo is the most sensitive monostatic dish in the world. So they can see things that Altair never can. They're finding very many interstellar particles. So the really small, really fast ones that Altair is missing, Arecibo's picking up. So some really exciting results coming from there. The other radar that I've used is up at Boston, Massachusetts at MIT Haystack. This was from my days in MIT Lincoln Laboratory. And also over in Sweden, a radar called IceGat. So again, these are radars that are usually used for many different purposes, but we're using them now to look for these very weak signals that frankly we can't detect any other way other than these huge multi-million, billion-dollar radars. So a real-time snapshot of that movie that you just saw is here. This is what's called an RTI, or range time intensity profile. On the y-axis is altitude or range, on the x-axis is time, and it's color-coded for strength, so SNR is signal-to-noise ratio. And as you can see here, the sloped line is the head echo. That's the plasma immediately around the meteoroid. What's so great about head echoes is that they move with the velocity of the meteoroid. So right there you have already one observable on the meteoroid. But as you could probably see just from this image, the signal strength is really weak. So again, you need something like an Arecibo to be able to detect it. On the right, extending from the head, is the trail. And these are stationary, or they move with the velocity of the neutral winds. So think 100 meters per second or less. So the head echo is going 60 kilometers per second. The main velocity of the trail is due to basically atmospheric parameters. But they're much easier to detect. So there's a combination. There's something that's really hard to detect but gives you more information, something easier, but there's a lot more modeling to try to get out the parent properties of the meteoroid. Okay, so just to give you an idea of what we actually see, this is one meteoroid coming in. And what you see here is angle as a function of altitude, so it's a bit noisy. Again, these are really small, weak plasmas, so we're stressing the system. We're seeing just how sensitive we can get, and because of that, the data tends to be a little bit noisy. But we can see that we have an azimuth and elevation track. We have an interferometry system, so we can tell exactly where these particles are coming from. And this allows us to change the range rate, which is just the component of the velocity along the radar line of sight, to what's called a 3D trajectory, or actually allow us to get orbits. And through all of this modeling effort, we can then also determine things like properties of the meteoroid, the models I described earlier. So we can actually figure out what the mass is as a function of altitude, and for the first time, determine what the radius and density is as well. We believe these are the first ever results where we can not only tell you what the mass is, but also actually start to tell you what the composition is. Turns out that the NASA models that we've used in the past are wrong. Most of them assume a density of 3 grams per cubic centimeter across all meteoroids to do their impact assessment models. We're seeing a very big, wide range of meteoroid densities, all the way from less than 0.1 grams per cubic centimeter, all the way up to about 5 or 6. So we have to start changing these models if we want to do a true threat assessment with satellites. If we're looking at about 450 meteoroids, just to give you an idea of what we see, this is number as a function of different parameters. So the altitudes, the dark blues are very high frequency, the light blues are ultra high frequency. Again, we do see it primarily near 100, though they go all the way down to 80 and sometimes up to 130. They're going very fast. There seems to be a high velocity component, around 60 kilometers per second. The minus is just because it's coming toward us. But there also seems to be a lower velocity component as well. So this bimodal distribution we've seen both at Arecibo and at Altair. The radar cross-section is, again, the signal strength. You already saw this on the movie. But if you go lower in frequency, you're going to get less signal return back because we're scattering from a plasma. Yes? Sorry.
What does a velocity of 3 kilometers per second mean?
As far as what?
Well, I'm looking at the upper right-hand plot, and the blue bars are around 0. What does that mean?
Yeah, so this again is range rate, so it's the component of the velocity along the radar line of sight. Yep, so it's a good point. Yeah, it's the only one you get, but then you use the interferometry to actually get a 3D track like we do here. So red is what we measure with just range versus time, and then we use the angle data to convert the red to the blue. This gives you your 3D track. But as you can see, this is pretty noisy, so usually when I'm reporting speeds, I tend to give you the range rate because that's way more accurate than the 3D. That takes a lot more data massaging. But that's a good point, yes. We wouldn't expect anything below 11 kilometers per second because that's the escape velocity for Earth. Okay, so and then the radar cross-section, as I said, you go higher in frequency, you have less signal. And then on the bottom right, just to give you an idea just about how much energy is being deposited, we see decelerations all the way up to 500 kilometers per second squared. So these things are depositing their material. There's a lot of energy that's coming in all the time. And certainly this is the reason why we're seeing all these atmospheric effects that I mentioned before, such as heavy metal layers. Okay, so not published yet, but I find this very exciting. We and Arecibo are also, we believe, a lot of caveats here, detecting particles that originate outside of our solar system. And if you get up at a conference and you say this to the general meteor population, they'll tell you you're stupid. But I like to go back to the whole rise of meteoritics and how people would say, okay, well, these things don't even come from outer space. I hope that we're starting to blaze the path into saying how many particles actually come from outside our solar system. So if you just look at altitude as a function of speed and color-coded for mass, there is a subset of the population going greater than the escape velocity plus the Earth's orbital velocity with the very smallest masses that we are able to detect. And if you do some preliminary orbital analysis, okay, so you actually again take the 3D trajectories and figure out where they're coming from, there seems to be a clumping with Jamingo pulsar as well as beta Pic. Now, I'm not saying that this is in any way definitive or conclusive, but if you look in the astrophysics community, there is some suggestion that these stars, these pulsars, can eject actual macroscopic material. And if so, I mean, we're way outside of where we have to worry about Lorentz forces. So if we ignore things like magnetic fields, interstellar magnetic fields, then it's possible, of course, that those particles would actually intersect the Earth's surface. In situ measurements, such as Cassini, Stardust, Ulysses, Pioneer, have also said the same thing. The big difference is that they're at a much smaller size regime. So we're saying even in the nanogram, 10 to minus 7 to nanogram regime, there are interstellar particles coming here, which again has implications for life on Earth, because now we're talking about bigger particles finding its way through Earth's atmosphere, potentially hitting the Earth's surface. Yes?
What happens to the residue of the ionization trails when they condense? Where do they deposit out? Do they stay in the atmosphere for a certain length of time? What's the speculation?
Great question. Most of the trails recombine within about a second. Some of these dusty trails, so this whole area of dusty plasmas, can go on for many minutes, sometimes even hours. So when they linger that long, they create something called a sporadic E layer. It's a dense layer of ionization. They also create these heavy sodium layers. So yeah, absolutely, that it has a direct effect on what's happening at that altitude. It just depends on how big the particle is and whether it has this dusty component to it. Yeah.
Is the solar wind any interference from that, or is that a higher altitude or different frequency so it doesn't corrupt your data?
No, great question too. Solar wind will absolutely have an effect. It all depends on the charge to mass ratio of these particles and if the particles are charged. In fact, one of the students yesterday just asked, well, are these particles charged? And if they are, certainly then they're going to have Lorentz forces around the magnetic field. We don't know yet. We don't know if they're charged or not, but depending on the size, then you do have to worry about solar wind effects.
Does the evidence for interstellar meteoroids show up just as clearly in the range data when that's all used?
No, because the range data, we do see particles still going greater than 73 kilometers per second. But even though I'm showing velocity here, where I really make the cutoff is eccentricities greater than 1. And I can't get an orbit without using the interferometry, which means by definition I'm using the 3D velocity. So there are a few that are greater than 73 kilometers per second if we just use that velocity, but it's really the orbits that determine whether it's interstellar or not.
The satellites in the past that have been designed to pick up deposition like LDEF,
Yes.
what has been the results of that in terms of the deposition?
Yeah, LDEF is great. The problem is that all of these in situ experiments can't really tell you where the particles came from. And they can tell you energy, but then you usually assume a velocity to back out a mass or vice versa. So we don't really have any conclusive evidence to show that LDEF ever detected interstellars because we don't actually know where the particles came from. Yeah. So I'm hoping we can come, this is an engineering challenge, and I'm hoping we can get beyond it, but we're not there yet. Okay. So I'm sorry, I'm talking too much over here. I'm going to finish just the last part of my talk with what I started with, which is if a meteoroid impacts a satellite, and so my PhD's in physics, right? So I always get drawn toward the physics part of it, but I'm in an engineering department, and of course we want to focus on some real-world applications, and one of those is when a meteoroid impacts a satellite, what can happen to it? As I mentioned, we know in the past that people have focused on mechanical damage. So if I know the size, if I know how big it is, how fast it is, and I know the properties of my target, if it hits, I know what's going to happen. What people don't understand is if it's really small that it won't penetrate, could it still ionize and form a plasma that could cause an electrical anomaly? So what you see here is a movie put together by one of my students, Nicholas Lee, who's in the front row, so if you have any questions, I'm going to direct it to him. But what you see here is just a cartoon of the impact, and then those white particles going up and down, those are electrons oscillating. So again, the same thing that's happening in the atmosphere, but now we're doing it on a satellite, forming a plasma that's then expanding. And as it expands out, the electrons go first. Okay? They're much lighter than the ions, and therefore they have a higher thermal velocity. But that ambipolar electric field pulls the electrons back to the ions. But then they get out again because they have a higher thermal velocity. So the whole thing's expanding, and then the electrons are oscillating around this ion boundary. That coherent oscillation could potentially be creating an RF emission. And this is where we've been talking to some people here at SETI, Bob Dahlgren and Friedemann and others, about how can we collaborate with you to understand the RF emission from impacts, which may be similar to things like RF emission associated with faults, with earthquakes. So what you see here is a model of how much charge is actually generated when a meteoroid impacts. And on the y-axis is mass, on the x-axis is the speed, and it's color-coded for charge. So more speed, more mass, more charge. But unlike with mechanical damage, with here it's all about the velocity. So it basically scales as v cubed, perhaps higher. Okay, so even if it's really small, if it's going fast, it's going to create enough charge to potentially cause an issue. My one equation, this is a plot of the modeled expected emission associated with a meteoroid impact. And I won't go into what the equation is showing, but if you just look at these three different curves, this is showing for low frequencies, think VLF and VHF, you have a lot of emission. And as you dip down in frequency, you dip down in power, and then it seems to increase again. And this is for three different types of particles, one that creates big oscillations, and therefore a bigger signal, and one that creates more oscillations, it has a higher frequency response, and then one that you can barely even see the frequency response in. So the idea is, depending on the properties of the parent particle, you can get a very different emission. But all the models seem to indicate a lot of emission in the lower VHF, and then a lot of emission again up in microwave. So models are great, but they don't really tell you anything. So what we need to do is actually do some experiments. So the project that Nicholas is heading up is we've gone once to the Max Planck Institute in Heidelberg, Germany. They have a Van de Graaff accelerator there, which accelerates femtogram particles up to about 60 kilometers per second. So the good news is that it can get up to meteoroid velocities. The bad news is it's femtogram when we're looking at microgram in space. Nevertheless, Nicholas and his team have built what's called retarding plasma analyzers, retarding potential analyzers, or these plasma sensors, as well as some RF sensors to measure the emission. And we've put different types of target in the chamber and basically shot it and then measured the response. Can we actually detect plasma from this size particle? And amazingly, shockingly to me, the answer is yes. Even femtogram particles will produce a plasma that we can actually detect with our retarding potential analyzers. So on the upper left here, you see a signal. This is 3 different velocities on the order of 4 to 6 kilometers per second. As a function of time, I think this was on the tungsten target that was floated. We could either charge positively or negatively or float it. And he used tungsten, aluminum, and aluminum foil. These are low-speed particles on the upper left. And this signature right here, which has these multiple humps on it, is from a high-speed particle. This hasn't even been published yet. We just submitted to a journal last week. But clearly there is a difference between a high-speed particle signal and a low-speed particle signal, even though all of them are producing plasma. And you'll see on the bottom just how often we are detecting signature as a function of the type of material. And the green is floated, and then the red is charged minus a kilovolt, and the blue is plus a kilovolt. So you see most times we're seeing more signal in tungsten than we are for aluminum or aluminum foil, mostly when it's charged. Again, this gets to spacecraft conditions. But again, we can't fully reproduce what's happening in space, unfortunately. Our capabilities on the ground are such that we're limited in terms of mass and velocity. So for projectile mass as a function of projectile speed, we can go to light gas gun facilities, such as the NASA Ames Vertical Gun Range, which we've looked at and hope to use. Or we can go to Van de Graaff. The problem is that light gas guns are too slow for meteoroids, and Van de Graaffs are too small. Now we can bound the problem. We can go to both places and try to get to this microgram going 60 kilometers per second, but there's no reason to say that it's going to be a nice linear curve that we can then extrapolate. So we really need to go to space. And to that end, we're proposing to build a CubeSat called Medusa, which, tongue twister here, stands for Meteoroid, Energetics, and Debris for Understanding Space Situational Awareness. You can tell I worked at national labs my whole life, because we always had to put like a really catchy acronym so people would fund us. Unfortunately, no one's funded us yet for this. So, but I think the idea really has merit. And we want to go to space for a number of reasons. We're never going to be able to fully replicate conditions here on the ground. And we could do it relatively cheaply. Yes?
Yeah, can you do anything on the space station?
Oh, great question. We were just at NASA Ames. Yes, we are looking at just putting some sensors, like plasma sensors and RF on the space station. Just started talking about this a month ago. I don't know, I've never done it, so I don't know how feasible it is to actually get something flown, but yeah. And again, the goal here is different than things like LDEF, is that we want to study the electrical effects. So we're going to have plasma sensors, which are these green sensors here, as well as RF sensors, which double as the booms that hold what is called the MMOD, or impact screen. Okay, CubeSats are small. They're 30 centimeters for a 3U, but we want to get hit. So we want to be as big as possible, which means we need to start looking at some deployable technology to make ourselves big so that we do get hit. If we do develop this 1 meter by 1 meter screen, which we hope gets hit, then the meteoroid would come in, form a plasma that would then expand over the CubeSat, be detected by these plasma sensors as well as the RF. And we would expect that we'd probably get hit about once a day with a nanogram-sized particle. But as you saw, we were detecting signal from femtogram-sized particles. You can extrapolate that you're going to have many, many more of those sizes hitting, but we just don't have the data right now to even say how many femtogram particles are even out there, because no one can see them. But because we're doing deployable, and everyone gets really scared when you say deployable because there's a high failure rate associated with it, we've been doing some testing on the ground to make sure the screen that we've developed will actually fully deploy once we're in orbit. So Nicholas had the opportunity to be a part of this FAST program, which allows students and others to get on these zero-G flights and test their experiments, to do some data. And he was able to do basically 80 parabolas, okay? So this is the program, again, out of Houston, which is about 15 to 25 seconds each. And he tested 2 different screen thicknesses, about 0.001 inches and about 5 times thicker, A lot of success in the thinner one. I would say moderate amount of success in the thicker one. And hopefully the movie works. You could see him in the zero-G flight deploying his screen. And you did not get sick, right, Nicholas? As far as, yeah, which is good. I didn't go on there because I would have ruined the experiment. So. He did ask me, and I said, no, it's really your experiment. It should be you. But he didn't realize it was because I was actually scared to get on the plane. So very successful, and we're hoping that we can, and this was done actually without any funding. This was Nicholas doing it on his time. So we're hoping that to get a small amount of funding to actually continue this research. Okay, now that I've talked way too much, I have a very short summary. There's 100 billion of these that come in every day greater than a microgram, yet there is so little we understand about them. There's a lot of people looking at meteoroids as they come into the atmosphere. There's some that are looking at interactions on satellites. This is where my focus is. We need more modeling, we need more experiments, and if we are, I love Star Trek, if we are going to do this final frontier, if we are going to go into space, if we're going to populate Mars, we need to understand the environment, and we just don't right now. So it's a threat, and we want to minimize that threat as much as possible. So I'll leave you with the peak scale fireball, which I'm sure many of you know about. This was back during the Draconids in 1992. And it's shot across the sky from Kentucky to New York. Many people thought they were aliens or re-entering space debris. Turns out it was a bolide. It was a big meteoroid. And it eventually, as you'll see, crashed into this person's car with very bad effects. Luckily, she wasn't in it. The sad story is that she didn't get to keep the meteorite. So the government took the meteorite. I don't know if it's on eBay. I don't actually know what happened to it. But the person whose car got damaged from it didn't actually get to benefit from the fact that she got hit by this huge meteorite that hit.
Your insurance rates went up.
Sure, yeah. I wonder if that's something you can opt for. I haven't even thought of that. The reason I bring this up is because the Draconids are expected to storm again this year in October. So NASA's sending many people over to Greece, I'm not one of them, to go actually measure these properties. So if you're staring out at night in October, look up because you may be seeing one of these Draconid fireballs. Okay, that's it. Thank you for your time.
Thank you very much for the wonderful talk. A quick question. Do you have any data pollution at all from very energetic cosmic rays?
Ooh, that is a good question. I don't know. We have a whole data set that we call non-meteors. Certainly some bits of debris in there, but I don't see any reason why we wouldn't be able to detect cosmic rays. It's the right frequency. It's creating plasma. Yeah, I don't know. It's a good question. I haven't looked. So if you're interested in the data, I could send it off to you.
And Sigrid, your possible collaboration with SETI, would
Yes.
that also involve the Allen Telescope Array and its capabilities?
Absolutely. Yeah, I have to say, I forgot to say when I first started that SETI is just such an inspiration for me and so many others getting into this field. So any opportunity to collaborate, I would really welcome that. So.
You mentioned previously about relationship of your testing to earthquake RF emissions. Could you elaborate on that?
I might turn this over to Bob. So we just started talking about this a few weeks ago on looking at RF emission associated with impacts that I showed as well as earthquakes. Now, I'm not an earthquake expert, so Bob, could you talk, or Friedemann, a little bit more about this?
We do see strange phenomena which seem to be connected to the fact that suddenly we get a plasma state in the solid which expands out from within the Earth, breaks through the surface of the Earth and gives a flash that typically lasts up to about a second. These are known as earthquake lights. And we are very interested in understanding what is really going on. How can you suddenly get an electric outbreak from the solid Earth? And we know where these happen. We never know when they happen, but we also know the geology that seems to be connected to the frequency of such earthquake lights. There are other forms of earthquake lights in addition, but this is one particular form that we would be very interested in understanding.
Thanks.
Hi. Have you been tied in with the AMS satellite?
Mm-mm.
You ought to.
Okay.
Alpha magnetic spectrometer.
Okay.
Instrument that's going to the ISS.
Okay.
It's going up on the shuttle this next launch.
Okay. Nicholas, do you know about this or? Okay. All right. Thank you. We'll look
My
into it.
question is about the femtogram. If there are femtogram component to the interstellar dust, at some small mass, wouldn't the solar radiation pressure keep it all at bay? And what is that small mass cutoff?
Yeah, that's beta meteoroids. The particles are basically being pushed out from solar radiation pressure. It's right around that regime. So right around the femtogram regime is when things are just going to get pushed outside the solar system anyway. Yep, good point. Oh, yeah, so I didn't go into it, but there's all these sources in the sky for sporadic meteoroids. There's apex and north apex and south apex, and then there's Helian and anti-Helian sources. So we see particles coming from these sources in the sky that are still unexplained, but the Helian source may be the source of these beta meteoroids, although it's at a much different size regime.
Sigrid, I'll just stick in a question before you, bud. Stardust collected cometary dust, and they were able to analyze that using gel
Right.
and look
Using the gel.
and get isotope ratios of elements in the particles that they collected in their gel.
Right.
Is this a possibility that you might be able to send up some gel-like substance and collect at the same time that you're getting these interplanetary
It's a great idea.
showers or something like that
I think
to
you're right. I
verify
think
your hypothesis?
we need a combination of technology. The aerogel is great because it captures the particle. It just doesn't give you, unless you have a velocity vector track, which most times you don't, you can't actually figure out where it's coming from or what the mass velocity is independently.
You could do isotopes to tell what it's like.
That's right. So if we could somehow come up with different types of sensors to not only measure the different isotopes, which you mentioned, but also figure out definitively where it's coming from with what mass velocity, that would solve the problem. So, yeah.
Have any of the manned spaceflight missions experienced meteoroid strikes? And statistically, how lucky are we that we haven't lost astronauts to meteoroid strikes?
Oh, yeah. Good. Yeah, guys have great questions. Yes, there is a story about the Russian cosmonauts during, I think it was the Perseid 1993 shower, getting freaked out, excuse my terminology, because they all of a sudden heard all these tiny pings. So this was on the Mir, and I think this was back in 1993. The thing that kind of surprised us is we knew the shower was happening, but we didn't think that it would be so prevalent at the smaller sizes that we would have to worry about our manned missions. So this was kind of a wake-up call to us that even though we on the Earth can't detect those sizes, up in space they're being hit by it. So I'm going to give you a bad answer. I don't know how dangerous it is or how lucky it is that an astronaut hasn't been hit. I do know that when they get outside the space shuttle, that they always put themselves in such a way as to protect themselves from meteoroids coming in. Like they use the shuttle as a shield. And they don't launch during major showers. Yeah. But I don't know. I don't know how lucky we are. Yeah.
You mentioned that these meteorites will probably carry a charge. And in your experiments from the Max Planck Institute, you applied a plus and minus 1 kilowatt bias. Can you do, under these conditions, probably the projectiles were already charged?
Exactly. They had to be charged, right?
In order to accelerate.
It's in order to accelerate. I glossed over it, yes, but the projectile itself is charged, which I feel is a more accurate representation of what actually happens in space. So definitely the interaction between a charged particle and a charged target is something that Nicholas is just now starting to dive into. Yeah.
Okay, I'd encourage you all to come up after the talk to our speaker and we have a special
Yay!
antique SETI mug.
Oh, I love it. Thank you.
And if you'll all join me in thanking Sigrid for a great job.